afternoon, everyone. Okay, so welcome to our midterm revision tutorial. Okay, so we are going to be going through quite a lot of questions. Okay, 30 questions, so it will be quite intense and maybe tiring session. So we will try to do about half the questions first, and maybe we'll take a short break and then we'll come back and continue. Okay, so in that case, we won't be so drained out. Okay, so I hope you have attempted the questions. All right. So if you've got the right answer, then we can confirm, all right, whether the approach is correct. And if you're not sure, hopefully this session clears up whatever that is still you're not still clear about. Okay. Okay, so let's get started with the first question. Okay, then in the break we can talk about other things. Okay, so so all these questions that you see are from the past year midterms. Okay, so these are the exact questions that your seniors have sort of solved during their midterm. All right, so it sort of gives you a good gauge on what we've been asking and what kind of concepts that you're expected to know. Okay, so let's start with question 1. So here you can see 2 branches. Okay, one branch of resistors with 40, 30, 20, 60, 50, 70, and so on. Right? And then you have another branch over here where which is just 10 ohms. Okay, so if you recall your parallel resistors, okay, if I have 2 resistors, RA parallel with RB, okay, whenever I have RA parallel then to RB, okay, if we say that RA is smaller than RB, okay, then this total resistance RT will always be smaller than the smallest resistance. Okay, you would have seen this, okay, when I do calculations. All right, and even if you sort of measure, you'll also observe the same thing. The combined resistance, okay, for parallel branches will always be smaller than the smallest resistance. So you can see that over here I basically have 2 branches. All right, this is one branch and this is another branch. All right, so technically when I look at this, regardless of what value I have on the top, because my bottom resistor is 10 ohm, I can say for a fact that the total resistance will definitely have to be less than 10 ohms. Okay, which means that I will straight away know that the answer is A. Okay, so of course, if you go ahead and calculate everything, you will still get the same answer. All right, but by analysis and our understanding of how parallel resistors are calculated, okay, you can straight away say that based on the 4 options, A is the only option that satisfies this criteria. Okay, so that's why the answer is A. Okay, so again, you can see that if all your concepts are clear, you can use that to quickly solve the questions. If not, you might spend time doing a lot of unnecessary work. Okay, like in this case, if you go ahead and try to solve for the branch, okay, then you will just waste a lot of time. Okay, so let's so I hope this is clear. Yes, before I will continue, okay, with all the discussion, if you have anything that you're not sure, just feel free to ask, okay, in the chat, or you can unmute and ask in the mic. Okay, so here we have another circuit. So you have RA and RB in series, and parallel to RB, we have another 2 resistors. Okay, and what we want is we want to make a voltage divider such that V1 is 6 volts. Okay, and V2 is 2 volts. All right. So of course, if you just think of it as just RA and RB, okay. So if I were to redraw this circuit and say that this is RA and this is RB. Okay, and what I want here is I want 6 volts here. So if I have 6 volts here, that means there will be 4 volts here. Correct? Okay. And if I look at all this combination of RA and RB, okay, all the values will work. Correct? So if I have 40 and 60 is also fine. If I have 400 and 600 is also fine. Okay, that is if the circuit was only RA and RB. Okay, but now I have another branch. Okay, this branch here that has RC and RD parallel to RB. All right, so we need to now see what is the effect of RC and RD on RB, or the total resistance of this two branches here in parallel. Okay, now let's just look at this branch and let's do some calculation first, and then from there we will sort of understand the theory behind it. Okay, so if I look at this two branches, I have RB and I have RC and RD. Okay, now let's assume that I take RB to be 60. Okay, so I have two possible combinations. Correct, the one is 400 and 200, or the other one is 4,000 and 2,000. Okay, so I'm just taking option A and B just to see what happens. Okay, so now if I look at these two options and I calculate, okay, so we can see that the combined resistance in this case, okay, the total resistance here would be 60 parallel with 600. Okay, and that will give me 54.5 ohm. Okay, whereas if I were to do this, RT will be 60 parallel with 6,000. Okay, so sorry about that. Something is seriously wrong with my laptop. I'm trying to prepare another one on standby. Okay, so is it okay now? Can you all see my screen? Hear me? All okay? Okay, thank you. Hopefully there is no other disruption. So okay, so let's just continue. All right. So here, yeah, if you look at this branch over here. So as I was talking about this, so sorry about the delay. Okay, for this, if I were to look at the possibility of 60 parallel with 6,000, then the total resistance will come up to about 59.4 ohm. Okay, so what you can see is again similar to the question one, where I have two parallel branches. So I'll always be smaller than the smallest resistance. Okay, but not only that, when the two parallel branches are more distinct from each other, so you can see that 60 parallel to 600 and 60 parallel to 6,000. So the difference is magnitude of 10 greater. So when the difference between one branch and the other branch is bigger, then you become closer and closer to the smaller value. All right, so that ensures that the voltage divider principle still holds true regardless of the parallel branch. Okay, so that is actually what we call the loading effect. Okay, and why we see the loading effect is because when the two parallel branches combine, they create a new resistance, correct, which you need to factor in, all right, which will then affect the voltage divider that you apply for the first circuit. All right, so because of that, okay, the correct combination here would be B. Okay, why? Because in B, when you say 40 and 60, on the other branch you have 4,000 and 2,000, which means that this combined branch between 60 plus 4,000 and 2,000 will be approximately 60 ohm, which means that I will still get about 6 volts, close to 6 volts, and again, when I have 6 volts here, I'll also get a 6 volts here. Correct. So when I do a voltage divider between 4,000 and 2,000, I'll get the 2 volts here. All right, so that is the idea behind question 2. Okay. Okay, question 3 is actually sort of again tying back with the same idea of question 2, in a sense that, and question 1 also, that when you have two parallel branches, then you're always closer to the smallest resistance. All right, so if you look down here, what you see is this branch over here is basically 100k times 2, right? 100k plus 100k. And this is going to be far greater than the 1k, which means that effectively when I try to simplify the circuit, I can say that 1k parallel with 200k is going to be almost 1k. Correct. Then when I look down here, it will be 1k in series with another 1k. That means it's approximately 1k times 2. And that is also significantly greater than the 10 ohms. Okay. So which means that when the 10 ohm is parallel with this 2k, it is also going to be almost close to the 10 ohms. Correct. So with this understanding, we can sort of say that the voltage, okay, across the 10 ohm is going to be approximately 30 volt. Okay, very, very close to 30 volt. Similarly, the voltage across the 1k ohm will be also very, very close to 15 volt. And the voltage across the 100k will be very, very close to 7.5 volt. Okay, so even if you were to manually calculate step by step, you will also get the answer to be almost close to 7.5 volt. Okay, because it comes back to the same idea as before. When I have two parallel branches, I'm almost close to the smaller branch, especially when the difference is very great between the two branches. Okay, so by that observation, you can sort of quickly narrow down and actually get the answer at 7.5 volt. All right, but again, if you calculate also, you will get the same answer. But I guess this will be probably a quicker way to solve this. Okay. Okay, so let's move on to question 4. So in question 4, basically what you have is you have a 10 volt. Okay, let me this one. 120, 120. and R. Okay. Yeah, somebody has a question. No. Okay, so when I look at this, what is the value of R that will result in a current of 0.1 ampere passing through R? Okay, so what the hint given is you need to find the Thevenin's equivalent circuit. All right. So to find Thevenin's equivalent, basically you need to find VTH and RTH. All right. So let's just simplify this first. So you can see that when the current comes here, okay, from here it will split into this branch and this branch, correct? And when it's split into this branch and this branch, and over here what happens is this is a short circuit part. That means the current that comes through the left side and the right side will eventually merge here and then split again into 40 and R. Okay, which means that I can sort of redraw this circuit, okay, as two separate ports here, 120 and 120, and then another 40 and R. Something like this. Okay. So we know that 120 and 120, if I combine, will be 60. So this will be 10, 60, and I have a parallel branch of 40 and R. So this is where the R is. Okay, so the first step is, of course, you simplify to get this circuit. Now the next step is to find VTH and RTH. All right, so the VTH is the open circuit voltage. So since part where I'm looking at, so technically I only have a series pathway between 60 and 40. Okay, so VTH is equals to 40 over 100 times 10, which will be 4 volt. Okay, so to find RTH, okay, as I've said before, you imagine there is an imaginary source there. So if I put an imaginary source there and I trace how the current will flow, it will flow through the 40 ohm. At the same time, there is a branch to the 60 ohm. Okay, and then there's a short circuit over here, back. So the flow of the current would be over here, I will split. So at this point, I will split into 40 and 60. So since I split into 40 and 60, I can say that RTH is, okay, so let me continue this question first over here, okay, since it is seems to be okay after a while. Okay, so what is the value of R that will result in, okay, so what we did is we calculated VTH. Okay, next is RTH, guys. So RTH is 40 parallel with 60. Okay, so 40 parallel with 60, what will we get? 24 ohm. Okay, so if I were to redraw the circuit over here, I'll get 4 volt with 24 ohm, and RTH is here. Okay, that is your R. Okay, so so by Ohm's law, we know that I is V by R. So I want a current of 0.1 ampere to flow with 4 over 24 plus R. Okay, so R will be equals to 16 ohms. The answer is D. Okay, so this question here is similar to the earlier question. All right. What will result in a current of 0.15 ampere passing through R? So the same thing. So if you look at the circuit, you have 9 volts here, and you have 60, and then you have another R, and this is, again, you can split it up into 60 and 60. Okay, so that will give me 60 parallel to 30. So this I can simplify this to be a 30 ohm resistor, because 60 parallel to 60. All right, so again, I do the same thing. I need to find VTH and RTH. All right, so VTH in this case would be the Thevenin's open circuit voltage. So it would be 60. So since it's just a series circuit, 60 over 90 times 9, which will give me 6 volt. Okay, for RTH, again, the same thing. Imagine that I put a supply here. All right, so what will happen is, okay, so maybe I draw it separately here. Okay, so I have the R that I put a supply here, and I have a 60 ohm. Okay, then over here I have another 30. Okay, so it's basically two separate branches, correct? Because this is considered one branch and this is considered another branch. So it is 60 parallel to 30. Okay, which will give me 20 ohms. Okay, then you redraw the circuit. So you have 6 volts here, 20 ohms here, and then your R is over here. So the current 0.15, which is what you want, over the voltage 6 over 20 plus R, which will give me R to be 20 ohms. Okay, so the answer is D. Okay, so we'll go on to the next question. So in this next question, they ask what is the maximum power to be utilized by load R. Okay, so whenever you see these kind of terms, correct, maximum power, you straight away know that you're supposed to use the Thevenin's equivalent. Okay, that means you're supposed to find VTH and RTH, because the maximum power will only be delivered when the load resistance is equivalent, okay, to the sort of Thevenin equivalence resistance. All right, so basically what you need to do is you need to redraw this circuit, okay, with the load removed. Okay, so once again, I apologize for all this delay. I do not know if my PC will last again till the end, but whatever happens, I will still log back in to continue. Okay, but if you decide to log off, it's fine. You can watch the video later. Okay. I don't know. My laptop has been a bit unstable recently, but today has been extra over the board. Okay, so we have this circuit. So what we need to do is, in this case, we remove the R, correct? Because that is the load. And we need to find the Thevenin's equivalent. So the first thing is, I mean, we can do either one. So let's say I take VTH. So VTH is the open circuit voltage, correct? Now, when I look at this circuit over here, if you look at this branch, okay, this branch, even though it is a line that is shared between the sort of the upper circuit and lower circuit, there is no component here that causes any voltage drop. So because of that, okay, we can treat the upper circuit and the lower circuit as two separate ones. Okay, we don't need to worry about any interference. Why? Because whatever current that is coming out here is the same current that is going to come here, and it's only the that current that is going to flow through here and here. So there is no influence by the 10-volt source in the current that is going to flow through into the 20 ohm resistor. Okay, so you can effectively separate the two circuits. So the VTH is actually nothing more than the open circuit voltage that is parallel to this 10 ohm resistor. So imagine that this branch, this 20 ohm branch, is not there, correct? Because it is considered open circuit. So this VTH is the same as the voltage across the 10 ohm resistor. Okay, so the VTH in this case is basically 10 over 20 times 10, which is 5 volt. Okay, for the RTH, okay, for the RTH, again, what we're going to do is we're going to redraw the circuit. Okay, so I'm going to redraw the circuit here and put an imaginary source here. Okay, so now when I analyze how the current is going to flow, it's going to come out here. Okay, it's going to go to the 20 ohm resistor. Okay, sorry, I forgot to short circuit this. Okay, so this is now replaced with a short circuit. This is a short circuit. This is a short circuit. Okay, so when the current comes out of the imaginary source, it goes to the 20 ohm resistor. It splits into the 10 and 10, and whatever current goes to the 10 and 10 will come back here to come through here. Okay, so that same current that goes to the 10 and 10 is what is going to come back in to the voltage source or this imaginary source. Okay, so the RTH is basically 20 plus 10 parallel with 10, which will be 25 ohm. Okay, so the circuit is now sort of simplified into 5 volt with 25 ohm. Okay, and that is your R. So for maximum power is basically you can use the same formula as I square R. So 5, the total current will be 25 plus 25, correct? When R L is the same as RTH, I square R times 25. So that will give me 0.25 watt. Okay, so that is your answer A. Okay, question 7. For the circuit shown in the figure above, what is the current? Where's the value of current I1? Okay, so as you can see, current I1 is basically a line that sort of connects between the upper circuit and the lower circuit. All right. So it is a combination of whatever current that is flowing here in this branch through the 4 ohm resistor, plus whatever is coming through the 20-volt source and the other resistors here. Okay. So what we need to do is we need to sort of figure out these two currents and then see the combined effect. All right. So as I said, like similar to the earlier circuit, this common branch, there is no resistor. That means there is no voltage drop occurring here. So in that sense, you can say that the current that flows through the 4 ohm resistor is going to be a result of only the 8 volt supply. Okay. So this branch here, okay, this red color branch here, this current is only a result of the 8 volt. Okay, so that current, which I can call it I1, will be 8 volt over 4 ohm, which is 2 ampere. And for this 20 volt supply, okay, the current that flows will be a result of that supply and these other remaining resistors. Okay, so that I2 will be equals to 20 over 4 plus 20 parallel 80. All right, because the current that comes through here will split into here and here, 20 and 80. So 20 and 80 are parallel. Okay, so that will give me a 1 ampere. Okay, so by KCL, we know that two currents coming in and I1 is the current going out. Okay, so maybe I should call this I3 since that one is I1. Okay, so I1 is basically I2 plus I3, which will be 3 ampere. Okay, so let me move on. Okay, question 8. So you have a current of 8 ampere flowing through a resistor network, and you have to find a voltage difference between X and Y. Okay, so if you want, you can sort of redraw it. Okay, so I'm just going to redraw it just to show it a bit more clearly. So you have a 12 ohm, then you have a 2 ohm here, and another 6 ohm here. And here you have another 4 ohm, another 4 ohm. Okay, so if you look at it, it's basically, in a sense, if I combine it, you can see that the top branch is 8, bottom branch is 8. Correct? So it is basically 8 and 8 parallel with 12. So I can redraw it one more time to say that this is actually equivalent to 12 parallel with 4. Okay, this 4 is basically 8 parallel with 8. Okay, so that is what you get here. Okay, so since I know the current coming in is 8 ampere, this current here, okay, is equivalent to, if I use current divider rule, it will be 4, okay, over 4 plus 12 will be 16 multiplied by 8, which will give me 2 ampere. Okay, so if the current coming into this 12 ohm branch here is 2 ampere, and the other two branches have the exact same resistance, then that remaining current will be equally split, correct? So total current is 8, 2 comes here, balance 6. So I know that 3 will come here, another 3 will come here. okay, because both these branches are the same. Okay, so with that you can actually solve. This is your x, correct, and this is your y. Okay, and we can just take this point here as 0 volt reference, correct, since we don't know the actual voltage. So whatever the voltage here, let's say is 0 volt, since 3 ampere is going through the 2 ohm resistor, so it is 3 times 2 is 6 volt. So I have a minus 6 volt here, and 0, so 3 ampere and 4 will be giving me a minus 12 volt here. Okay, so the total voltage Vxy will be equals to minus 6 minus 12, which will give me 6 volt. Okay, question 9. Okay, question 9 is a bit similar. Okay, it's actually easier. Why? Because you can see that all 3 branches are the same. Okay, the top branch is 12 ohm, middle branch is 12 ohm, bottom branch is 12 ohm, which means that 3 ampere will basically split into 1, 1, 1. So I got 1 here, 1 here, and 1 here. Okay, so it's the exact same thinking. So 1 times 4, this will give me minus 4. 1 times 6 will give me minus 6. So minus 4 minus 6 will give me 2 volts, which is 8. Okay, so it's the exact same sort of question. Okay, but it's easier because the branches are all the same. So you just divide the current equally. Okay, question 10. Okay, suppose load resistance Rs is played. What is the maximum? So again, whenever you see this kind of statement, is already a clear indication that you're supposed to use Thevenin's equivalent. Okay, so in terms of VTH, okay, so if I want to find VTH, is the open circuit voltage, all right, which is voltage across this branch. So I can combine 8 and 8 to be 4. Then this will be 10 volts, and this will be 1. Okay, so the total, so the voltage VTH, I can take it as a voltage divider rule, which is from here to here. So it will be equals to 4 over the total resistance will be 5 times 10. So that will give me 8 volt. Okay, so that will be VTH. For RTH, again, we do the same thing. I imagine a supply here. Okay, so I have 1 ohm here, 8 ohm here, and 8 ohm here. Okay, so RTH is equals to 1 parallel 8 parallel 8, which will give me 0.8 ohm. Okay, so the final circuit here is 8 volt with 0.8 ohm. And for maximum power, this is also 0.8 ohm, correct, for RL. So the power will be I square R, 0.8 plus 0.8 multiplied by 0.8. And that will give me 20 watts. Okay, so you can see that these are all quite similar, okay, to the questions you have seen in the tutorial also. Okay, so it's just coming back to the basic concept. Okay, as long as your concepts are clear, you just apply them, okay, to find the solution. Okay, question 11. Find the Thevenin equivalent. Okay, so to find the Thevenin equivalent, basically we open circuit this. So you have 160 volt, 10, 20, 30, 100 volts. Okay, this is the open circuit voltage. So this open circuit voltage is basically the voltage, okay, at this point here, correct? At this point here, this is the open circuit voltage, VTH. Okay, so how do I find this? So you can apply your KVL. Okay, so by applying KVL to this loop, we can say that the current that flows in would be 160 minus 100 over 30, which will be 2 ampere. So if 2 ampere is flowing in this loop, then I can say that 2 times 10, which means there's a 20-volt drop here. Okay, so if the 20-volt drop across the 10-ohm resistor, then VTH will be 160 minus 20, which will be 140 volts. Then to find RTH is the same thing. I'm going to put in. Okay, so I'll have 10 ohm, 20, and 30. Okay, so if you look at how the current will flow, the current will flow here. The current will flow here. From here, it will split into here and here. Okay, but over at this point, okay, if you remember what we said, the current will always take the easiest part. So when it reaches this junction, it sees that the short circuit path back to ground, which means it will totally bypass the 30 ohm. Okay, totally bypass 30 ohm, and the resistance would basically be 10 parallel with 20, which will be 6 and 2/3 ohm. Okay, so that's how you get your answer here, 140 volt and 6.67 ohm. Okay, question 12. Find the Thevenin's equivalent circuit as seen by load RL. So basically what they want you to find is this VT. So when I remove RL is no longer in the circuit. Okay, so if you just redraw it. Okay, so this is basically your VT, all right? So you can use node analysis, correct, to come up with the equation. So you can say that if this point, all these points are the same point, correct? So I can take this as a common point, and using this as a common node, I declare or express the equations as all the current going in or going out, correct? So I can say 6 minus VT over 6 plus 4 minus VT over 4 plus 3 minus VT over 3 will be equals to 0. Okay, so then the rest is your normal maths already. Okay, but then VT equals to 4 volts. Okay, so the key thing is you can use your node analysis techniques to solve this. Okay, so that is how you find the Thevenin's equivalent. Okay, question 13. Okay, so another Thevenin's equivalent circuit as seen by load RL. Okay, so they only find the Thevenin's resistance. Okay, so not the voltage, Thevenin's resistance. So to find Thevenin's resistance, we remove the load RL. So let's redraw the circuit. So I short circuit here, plus 4. Okay, so again, I'm going to put an imaginary supply here. And how will the current flow? Okay, so it will flow through the 2 ohm, but when it comes to this branch, you will see that there's a 2 parallel branch, correct? One is a short circuit, the other is a resistive branch. So whenever there is a short circuit across any resistive component, it will straight away bypass those components. So it will straight away take the short circuit and go back through the 4 ohm. So the RTH in this case is basically 2 plus 4, which is 6 ohm. Okay, so that's how you get the answer here. Okay, question 14. What is the voltage VA? Okay, so to solve this, you can again use Thevenin's equivalent. Okay, or you can use node analysis, up to you. Okay, if I use node analysis, all right, I can say this is your VA. And I can express it as all the current either going in or going out to be equal to 0. Right? So I can say VA minus 15 over 2 plus VA over 5 plus VA minus 10 over 1 equals to 0. Okay, so that is one way in which you can express it. Then you can solve it. Okay, so the rest is, I'll just put it here. So you get VA is 10.29 volts. Okay, which is D. Okay, so I think quite similar to our tutorial question. Okay, so this is again follow on from the earlier question. For the circuit shown, the 10 volt voltage source is it supplying or consuming? So basically, the idea is simple, correct? If the current is flowing out, it is supplying. If it's flowing in to the power source, then it is consuming. So in this case, VA is 10.29 volt, correct? So we know that this is 10.2 now, 10.3 volt. So if this is 10.3 volt, okay, and this is 10 volts, we know the current is flowing in. All right, so how much is this current? This current will be 10.3 minus 10 over 1, which is 0.3 ampere. Okay, so current is flowing in, so it is consuming power. How much power? It is IB, which will be 0.3 times 10, which will be 3 watt. Okay, so the correct answer is C, consuming a power of about 3 watt. Okay, so that is that. Okay, so previously I said we'll take a break, but I think we already take a lot of break just now with all the technical issues. So I'll continue. All right. Yeah. So if you want to take a break, you can take a break and come back, and then you can just watch the video for that, maybe that portion of what I missed. Okay, but I think it's better that we continue so we don't overshot the timing. Okay, so for this circuit, the 10 volt source, is it consuming power or is it supplying power? So again, comes down to okay, why the is a question, why the current over the supply is same as the current over the resistance? Okay, so this is basically the current through the resistance, which basically because of the voltage difference, correct? So this is 10.3, this is 10. So we calculate the current as 0.3. Okay, so for this, what we can do is again we can calculate the current. Okay, so we can draw a loop here. So this current I will be 15 minus 10 over 2, should be 2.5 ampere. Okay, so that is the current flowing in that branch. Now we know that this point here is 10 volt, correct? And which is the same 10 volts across the 8 ohm resistor. So since the 10 volt across the 8 ohm resistor is fixed because it's parallel to the source, so we know that this current is 10 by 8, which is 1.25 ampere. All right, so 2.5 ampere is coming here, and 1.25 is going into the 8 ohm, so another 1.25 is coming here. Okay, so with that we can say that it is consuming power, and the power is consuming is IB, which is 1.25 multiplied by 10, which is 12.5 watt. The answer here is A, consuming a power of 12.5 watt. Okay, so question 17. So what is the voltage VA? So again, we can use node analysis. So this is VA. So if this is VA, this point here is VA minus 17. Correct? And this point here is VA minus 10. Because just like how we declare it before the supply, then we say that is that voltage plus the supply. So now we declare VA as a one after the supply. So before the supply, it is a subtraction. Okay, then we can again put in the nodes or put in select a node and put in the equation. So we can say that VA minus 17 over 2 plus VA over 5 plus VA minus 10 over 1 will be equals to 0. Okay, then the rest is just a normal math. So you'll get 10.88 volt, which is 10.98. Okay, so that is your 17, question 17. Question 18. For the circuit shown, what is the voltage V1 with respect to ground? Okay, so if this is V1, okay, so we can say that this point here is V1 plus 12. Okay, V1 plus 12. And what we can do is we can declare a node. Okay, so we can declare this as a node to come up with the equation. So we can say that all the current flowing into the node is 0. So you can say that V1 plus 12 minus 10 over 1, which is this current here. Okay, plus V1 minus 0 over 4, which is this current here. Again, we can say add up to 0. Okay, and then from there you can solve to get negative 1.6 volts D. Okay, so this is one way in which you can use node analysis and put in the voltages to find the unknown V1. Okay, question 19. What is the maximum power that can be utilized? Okay, so again, whenever you see this, okay, we straight away know that it is the Thevenin's equivalent. Okay, the maximum power that can be utilized. So we need to find the Thevenin's equivalent circuit. Okay, so I'm going to redraw this circuit a bit. Okay, so you have a 10 ohm resistor here, 2 ohm resistor, 4 ohm, 2 ohm, 12 ohm. Okay, so that is basically what you have here. Now to find the VTH. Okay, so to find the VTH, I need to find what is the voltage at these 2 points, here and here. All right, so since we know that both this 4 ohm and 2 ohm is parallel with 10 plus 2, which is parallel with the 12 volt. That means the entire 12 volts appears here and the entire 12 volts also appears here. Correct? Because they are both parallel with the 12 volt source over here. Okay, so it is, if you want to redraw it in a more easier way to see, you can just say that it looks like this. 12 volt with 2 and 4 and 2 and 10. It looks like this. Correct? There are two parallel branches with 12 volt. So since the 12 volt appears across both of them, then you can just use a voltage divider rule. All right, so this voltage here would be 4 over 6 times 12. All right, that will give me 8 volts. Okay, and over at the top will be 10 over 12 times 12, which will be 10 volts. So the VTH is 10 minus 8, which will be 2 volts. Okay, so that is the voltage. Okay, the open circuit voltage across the load. Okay, how about RTH? Okay, so to find RTH, I'm going to again redraw the circuit first. So you have this 10, 2, 4, 2. Okay, so why is 4 over 6 and not 2 over 6? Okay, why is 4 over 6? Is because you're finding, whenever you find this voltage is with respect to the ground. If I take 2 over 6 means I'm taking this voltage, the voltage across the 2 ohm resistor. Okay, but this point here, I'm taking the voltage with respect to this. That means it's actually across the 4 ohm resistor. Okay, the voltage at any point is always with respect to ground, unless you are taking it across the component. So in this case, this point here is equivalent to the voltage across the 4 ohm resistor, which means it is this point to the ground. So that's why we take the 4 ohm. If we take the 2 ohm, that means it is from here to here. Okay, so the current that flows drops by a certain voltage across the 2 ohm, and whatever is balanced is what you see here. Okay, so for the RTH, again, this is the redrawing of the circuit, and then I have a short circuit part here. Okay, so how does the current flow? So the current flows here, okay, then it will split into 10 and 2. Correct, split 10 and 2. And after it comes here, at this branch, what will happen? It sees a pathway here, and it sees another pathway here. So it sees a branch here and it sees a branch here. That means there will be some current that split to the 4 and split to the 2. Similarly, whatever current come here, some will split to the 2, some will split to the other side and come back through 4. Okay, which means that effectively it is equivalent to splitting between 2 and 4. Okay, so the same current, the original current split first between 10 and 2, and again is split again between 4 and 2. Okay, so the total Thevenin equivalent resistance will be 10 parallel with 2, add with 4 parallel with 2. Okay, which will give me 3 ohms. Okay, so now with that you can have the final circuit here, which is 2 volts and 3 ohm. Okay, and this is your load. So the power will be I square R. So 2 over 3 plus 3 square 3. It will give me 0.33 watt. Okay, option A. Okay, question 20. Okay, so now, yeah, basically we are done with all the normal resistive based circuits. Now we're going to the capacitor and inductive circuits. Okay, so for the circuit shown in the figure above, the switch has been open for a long time and the current measured with emitter was 1 ampere before time t equals 0. At time t equals 0, switch is closed. Okay, so since the inductor, so if you analyze this, basically what you can say is at time t equals to 0 minus, your inductor is in steady state, which means it is a short circuit. Okay, and since the current is 1 ampere, so I at 0 minus is 1 ampere, which is the same as I at 0 plus. Okay, so at I equals to infinity, at I infinity, that means t equals to infinity, what happens? Now, when the switch is closed, okay, when the switch is closed, you create a branch, correct? But if you look at what is happening, you have a V here, you have an inductor, but the inductor is actually a short circuit, correct? The inductor is actually behaving as a short circuit because it is already in steady state. So even though I close the switch, okay, I close the switch, it doesn't actually make any difference because when the current comes here, all the current will only go here. It will bypass the 6 ohm resistor. So if it bypasses the 6 ohm resistor, basically there's no current flow. So if there's no current flow, the voltage drop across the 6 ohm resistor will be 0 volt. Okay, because for any short circuit branch, okay, the voltage drop is always 0. Okay, so the current at infinity is still the same. It is still 1 ampere. Okay, so that is question 20. Question 21. What is the time constant for the inductor's current after t equals to 0? Okay, so for this circuit, so after I close the switch, okay, that is where the transient behavior will be observed, right? Because before that, the switch is open. So when I close the switch, the transient behavior occurs. So we know that tau is equals to L by R, okay, for a inductive circuit. Okay, but this R is always the sort of Thevenin's resistance. Okay, that means we must understand how the entire resistance of the circuit is with respect to the inductor. Okay, so the inductor will now be viewed as the load. Okay, inductor will be viewed as the load. Okay, so what you need to do is to find this R or so RT, you need to find the Thevenin's equivalent. So I need to redraw this as 10, and now your inductor behaves like the load. Okay, so when I put this imaginary supply here, how will the current flow? It will flow through the 10 ohm, and this point it will split between 20 and 30. Correct. So the Thevenin's resistance is actually 10 plus 20 parallel 30. Okay, it should be 22 ohm. Okay, so the time constant in this case will be 3 over 22, which is 0.136. Okay, it is 8. Okay, so that is this question 22. In the circuit shown in the figure above, the switch was initially open for a long time. At time t equals 0, the switch is closed. What is the inductor's voltage at time t equals to 0.2 seconds? Okay, so the switch is initially open. Okay, so we can say that at t equals to 0 or t0 minus, okay, the inductor is at steady state, which means it is short circuit. Okay, so the current at 0 minus would be basically 10 volt over 10 ohm. Okay, all the current just flows through the 10 ohm resistor, which will be 1 ampere. And this is the same at I equals to 0 plus. Okay, now how about when current at time t equals to infinity? When at t equals to infinity, okay, or basically once the switch is closed, all right, the current at this point will split into this branch and this branch. Okay, which is basically two 10 ohm resistor in parallel. Okay, so the total current will be 10 over 5. Okay, 10 and 10 parallel will give me 5. So there will be 2 ampere. All right. So we know this. Now, before I put into the equation, we still need to understand that to use the time constant, it must be L by RT. So I still need to find the Thevenin's equivalent resistance here. So I replace my inductor as the load. This is my source. This is my 10 ohm resistor, and this is another 10 ohm resistor. So when I analyze how the current will flow, it will come out here, it will split into this branch and then go back. So RT is basically 10 parallel with 10. Okay, so the time constant is 1 over 5. Okay, 10 parallel 10 is 5. You give me 0.2 seconds. Okay, so with this, I can write the final expression, which is basically IT is equals to I0, which is 1 e to the minus t by tau, plus 2, which is I infinity, 1 minus e to the minus t by tau. So that will give me 2 minus e to the minus t by tau. And what I need to do is, I need to find the inductor's voltage at time 0.2 seconds. So first I can calculate the current. So I can calculate the current at 0.2 seconds. Okay, so if I substitute 0.2 inside this expression, I'll get the answer 1.63. Okay, so 1.63 is the current that is flowing through, okay, this inductor at t equals 0.2 seconds. Now we know that the to find the voltage across the inductor, I can take the source voltage, subtract the voltage at this point, which is basically the voltage seen by the 5 ohm resistor. So the voltage at this point is basically 1.63 multiplied by 5. Correct, that is the voltage seen at that point, which is the parallel of the two 10 ohm resistors. So the voltage across the inductor is basically 10 minus 1.63 into 5, which is 1.84 volt. Okay, so that's how you get the answer B. Okay, so there is a alternate way of solving it using differential equation, which I will show you. But if you not sure about differentiation, okay, because maybe some of you have done it already in math, some of you haven't, okay, then you don't need to worry about it. As long as you can use our standard equation to solve it, then it's fine. Okay, but the alternate approach, okay, the alternative approach is, if you look back at the notes, we know that VL is L di dt. All right, so if I understand, or if you know differentiation and you know the inductance value is 1, so I differentiate the current. So this is the current expression. All right, so if I differentiate this, I'll get 1 over tau e to the minus t over tau. And then if I substitute the time at 0.2 and the tau value inside, I will also get 1.84 volt. Okay, again, if you are not comfortable with differentiation or you're not familiar with it, just ignore this. This is just to show you that there is also another way you can do it. All right, but as long as you understand how to use the transient expression, I think that is already good enough. Okay, you can still solve it anyway. Okay, let's move on to the next one, question 23. Okay, so question 23 is, we have this circuit where at time t equals 0, the switch is flipped. Okay, and they want to find the capacitance current at time t equals 0.2 seconds. So let's see what's happening. So at t equals to 0 minus, we can say that the, okay, so at prior to t equals to 0, we only focus on the left hand side up to the capacitor, right? Because the right hand side switch is still open. Okay, and since the capacitor is already in a closed loop, which means the capacitor would have fully, or would have reached steady state. Okay, so we know the capacitor would have reached steady state, which means it is open circuit. Okay, so the voltage across the capacitor at 0 minus is equivalent to the voltage across the 10 ohm resistor. Okay, why? Because if you look at the circuit, okay, what you have is, you have the 20 ohm, you have the 10 ohm, you have the 30 ohm here, and you have an open circuit. Okay, so whatever voltage I see here is the same as the voltage across the 10 ohm resistor, because there's no current flowing through the 30 ohm resistor here, okay, because it's open circuit. So it is basically a voltage divider rule. And this is the same voltage again at VC0 plus. Okay, so that is 0 minus and 0 plus. How about infinity? VC at infinity. Okay, so if you look at the circuit at infinity, basically what you have is basically a capacitor that is going to be discharging through two resistors. Okay, 50 and 50. This is your C. So as long as I discharge in a closed circuit, okay, you know that eventually you'll go to 0 volt. That's like how you saw in the studio, right? Once you start to discharge, its current will discharge to the capacitor until there is no more charges left. Okay, so we can say that the VC infinity will be 0 volt. Okay, so before we move on to the expression, the next thing that we also need to be mindful of is the time constant, okay, which is RC. Again, you will always remember this R is the Thevenin's equivalent resistance. Okay, so in this case, if you look at it, if the capacitor is treated as the load, okay, and we put an imaginary supply there, whatever current that comes out here will split into here and here. Okay, which means that the resistance is actually a parallel of 50 and 50. So this tau is 50 parallel 50 multiplied by the C, 8 milli, which will give me 0.2 seconds. Okay, now we can put all of them into the expression. So we have VC, any time t is 10 to the power of e to the minus t over tau. Okay, so we don't need to have the other part because VC infinity is 0. So the second half we don't need to put in. Alright, so what we want to do is we want to calculate the time, the current at 0.2. So first we can calculate the voltage at 0.2, okay, by using this expression, and we'll get 3.68 volt. Okay, and since this 3.68 volt here is going to discharge through these two resistors, we can use Ohm's law to say I is V by R. All right, so you can say that the voltage is 3.68 divided by the resistance, which is 50 parallel 50, which will give me 0.147 ampere. So that is the amount of current that would be flowing out of the capacitor at 0.2 seconds. Okay, so again, I'm just going to show you the alternative, which is again using differentiation. All right, again, these are formulas in your handout. Okay, it's not new, but we didn't emphasize it. Okay, because we are focused on using the transient steady state equations. All right, but this is just the alternative. Okay, the alternative is I can calculate the current I as minus C dV dt. And since we already know the expression for V, all right, if I differentiate it, I'll get minus 8m dV dt. I'll get minus 10 over tau e to the minus t over tau. And eventually, when I substitute 0.2 inside, I will get the same answer as this, 0.147. Okay, so again, if you are not familiar or comfortable with differentiation, you can just ignore this. All right, you can still use the same transient expressions to solve for this. Okay, question 24. Okay, two capacitors are fully discharged initially, and at time t equals 0, both the switches are closed simultaneously. How long does it take for VC to reach 5 volt? Okay, so the first thing is we can see that two capacitors are parallel, which means the total capacitance in this case is 3 farad. Okay, now the next thing is to know how long it takes. Of course, we need to put it into the transient equation. So to do that, I also need to find the RT. So to find RT, I will replace this capacitance with the imaginary source, correct? And then I have my two resistors, 3 and 6. Okay, so that is how my circuit will look like, correct? Which is basically current splitting between the 3 ohm and 6 ohm. So the RT is 3 parallel 6. Okay, that will give me 2 ohm. Okay, so how about the BC? Okay, at 0 minus and 0 plus. Okay, so we can see that at okay, since the circuit is open, okay, prior to anything, there is no current flow, all right, and capacitor fully discharged. So BC at 0 minus and 0 plus is both equals to 0 volt. All right, there's nothing there. Now the other thing is VC at infinity. Okay, so at infinity, what happens? At infinity, basically both these capacitors are fully charged, which means they behave as open circuit. So if they behave as open circuit, then you can think of it as just current flowing between the two sources, correct? So the current flow will be in this direction because it's 10 volt and 7 volt. All right, so this is again similar to how you calculate like the two parallel batteries, correct? So the current, okay, this current I here would be 10 minus 7 over 9. Okay, so that is the current flow. So to calculate the voltage, okay, across the capacitor, which is across the two parallel branches. So the two parallel branches are either 3 and 10 volts or 6 and 7 volts. Okay, so since we know the current is flowing in this direction, okay, so this is plus minus, so this is plus minus, plus minus, plus minus. Okay, same like how we did the battery. Okay, so if I take the left hand side branch, in the opposite direction, so I subtract. If I take the right hand side branch, I add them up. Okay, so if I take this right hand side branch, the total voltage will be 7 plus IR. What is I? 10 minus 7 over 9 multiplied by the R. So that will give me 9 volts. Okay, so the VC infinity would be 9 volts. All right, so with that, I can have the expression for VCT, which is 9 1 minus e to the minus t by tau. And what I want is how long does it take for the voltage to reach 5 volts? Okay, so how long does it take to reach 5 volts? So I need to take this expression 9 1 minus e to the minus t over tau to be greater than equals to 5. Okay, so that is the basic thing. Then of course the rest is just solving it. Okay, so you have e to the minus t over tau less than equals to 4 over 9, and eventually you'll get t must be greater than equals to 4.87 seconds something. Okay, so the answer here will be A. Okay, question 25. The practical inductor. So the switch is initially open for a long time. At time t equals 0, the switch is closed while the practical inductor's voltage at time t equals 0.1 second. Okay, so since the circuit is open prior to time equals 0, I 0 minus is the same as I 0 plus, which should be 0. And when I close the switch, okay, at infinity, once inductor is at steady state, it is short circuit. So the current will be just 10 over 9 plus 1, which will be 1 ampere. So the expression for the current will be 1 minus e to the minus t by tau. All right, then I substitute inside 0.632 ampere. Okay, so the tau is basically 1 L over R. Okay, which is 1 over 10. Okay, total resistance in this case is 10 ohms. Okay, so once you know the current, okay, we know that that is the current flowing through the inductor at a time of 0.1 seconds, so 0.632. So to find the voltage across the inductor, I just need to take 10 volts minus the voltage drop across the 9 ohm resistor. Okay, so the voltage across the inductor would be 10 minus 0.632 multiplied by 9, which will give me 4.31 volts. Okay, so there's a few more questions, then we'll be done. Okay, so here we have a circuit where the capacitor was fully discharged initially and the current measured by the emitter was 2 ampere before time t equals 0. At time t equals 0, switch is closed. What will be the emitter's reading at time t equals to 5 seconds? Okay, so let's do this step by step. Okay, so the first thing is we know that prior to t equals 0, okay, the switch is open. So VC 0 minus is the same as VC 0 plus, which should be 0. Okay, at VC infinity, that means once the switch is closed, what happened is current will initially flow through the 2-3 ohm branches, but it will come a point of time where at steady state the capacitor will behave as a open circuit. Okay, which means that the only pathway for the current is here, correct, after the capacitor has reached steady state. So the voltage across the capacitor at that time is the same as the voltage across the 3 ohm resistor here. Okay, it's the same because it is already considered open circuit on the capacitor side. So since 3 ohm and 6 ohm are series, it's just a voltage divider rule. Okay, sorry. So before that, we know that at before time t equals 0, we know that the current was 2 ampere. Okay, and before t equals 0, since the current was only flowing through the 6 ohm and 9 ohm, this V is IR, which is 2 times 9, which is 18 volts. So we know that the total voltage or the unknown voltage here is 18 volts. So that's how you get 18 over here. Okay, so that will give me 6 volt for the VC infinity. Okay, now the next step is to understand the transient, correct? So again, whenever you talk about transient, you must always remember that the R must be the equivalent Thevenin resistance, correct? So if I were to redraw this circuit, okay, then I will have something like this. Okay, so this is the sort of capacitor which I removed, the 3 ohm resistor, another 3 ohm resistor here, and I have another 6 ohm resistor here. Okay, so from this imaginary source over here, where the current flows out, it will come here, it will pass through the 3 ohm and then split into this 6 and this 3. Okay, which means that the equivalent Thevenin resistance is 3 plus 3 parallel with 6, which is 5 ohm. Okay, so once you have found this, you can calculate your time constant tau, which is RC. Okay, in this case it's 5 and times 1, which will be 5 seconds. Okay, now to find the voltage across the capacitor, again, you also need to find the complete Thevenin's equivalent circuit. Okay? So we know what is RT. How about VT? So to find VT, we will again see that since this is open circuit, the capacitor open circuit, the voltage across the capacitor is the voltage across the 3 ohm resistor, which is actually your 6 volt. Okay, so if I were to just redraw it, so we know this is 18 volt, we know this is 6 ohm, and this is 3, and we know that this is already open circuit. So the voltage that I see here, VTH, is the same as the voltage across the 3 ohm, which is actually your 6 volts. Okay, so the circuit here I can redraw. I mean, the Thevenin's equivalent I can redraw as 6 volt, 5 ohm, and then my capacitor. All right, so since I already know the time constant, I can put the expression VC as 6 1 minus e to the minus t over tau, and I substitute 5 inside. Okay, for 5 seconds, I will get the answer as 3.79 volts. Okay, so this is the voltage across the capacitor at 5 seconds. Okay, so it is not complete yet. So we know that the voltage across here is 3.79 volts. Okay, so what is the next step? So we know that this is 3.79 volt. I can now calculate the current that is flowing in the circuit. That means that is coming out of the so the current is flowing through the capacitor. So this current I will be given as 6 minus 3.79 over 5, which is 0.44 ampere. So this 0.44 ampere is which current? It is a current that is flowing through the capacitor. That means this current. Okay, the current is flowing through the capacitor, which means that it is the same current flowing through this 3 ohm resistor here. Okay, so with that I can use Ohm's law. So I by R, I will get this voltage drop as 1.32 volts. Okay, so the voltage drop across the capacitor is 3.79. The voltage drop across the 3 ohm resistor is 1.32, which means that the total voltage drop here is the addition of both of this, okay, which will be 5.11 volts. Okay, that means the voltage here at this point here is 5.11 volt. All right, so now that I know that, I can calculate this current, because that is the current that would be shown on the emitter reading, correct? And that would be the actual voltage 18 volts minus 5.11, okay, divided by 6. Okay, and that will give me 2.15 ampere, which is this. Okay, so there are quite a few steps in this question. So we need to do it step by step. Okay, so the first thing is, of course, understanding the circuit behavior before and after. That means at 0, minus, 0, plus, and so on. Okay, then after that, it will be to find the Thevenin's equivalent circuit so that we know the voltage drop across the capacitor. Okay, and with that, you know the current through the capacitor. All right, and why you want the current through the capacitor is because then we can use that to find the voltage drop across the other 3 ohm resistor. Okay, and then we work backwards to find the current through the main branch, okay, or going through the emitter over here. Okay, so that is this. Okay, so we have the last 4 questions. Okay, these last 4 questions are okay. Again they are quite similar. Okay, two of them are similar, and the other 2 are quite similar. All right. So once we do one, the next one will be easy to do. So if you look at this, basically it is again going back to our complex numbers, our phasors, and so on. Okay, so what we have here is we are supposed to find the voltage source VT expression. We are given the voltage drop across, or the voltage expression for the capacitor. Okay, so this we can write it as 10 cos 100t is basically 10 angle 0 degrees, correct? Because there is no phase angle here. All right, then for this branch over here, we know it is Z and sorry, R here, and this is basically your ZC, all right, or XC. So this would be 1 over j omega c, which is again you can write it as, so what is omega? Omega is 100. Get this expression here. It's always written as cos omega t. So this is omega is 100. Okay, so if you calculate this, you will get it as minus j100. Okay, so to write this in phasor form is equivalent to writing it as 100 minus 90 degrees. Okay, because j is 90, minus j is minus 90. Okay, so if I look at this branch here, this entire branch and this entire branch both are parallel to VT, okay, which is my source. So it's just like how you would have an expression for voltage divider rule. I can say that my VC, okay, which is the voltage across the capacitor, is actually my ZC over R plus ZC multiplied by V. Okay, exactly how you would do it for a simple resistive circuit as well. All right, so with that, I can say that my VC, which is 10 angle 0 degrees, is equals to 100 angle minus 90 degrees over R plus ZC, which is 30 minus J 100 multiplied by V. Okay, so that is basically it. All right, the rest is all just your maths. Sorry, this is 104.4. Okay. Okay, then the rest of it, when you solve it, you will get it as V is equals to 10.44 angle 16.7 degrees. And to rewrite it in the expression, it will be V equals to 10.4 cosine omega is the same 100t, and this is the phase angle 16.7 degrees V. Okay, so you can see that it is similar to tutorial. Okay, the same voltage divider or current divider rules that we saw, only thing applying it to phases. Okay, question 28 is also very similar, where you're supposed to find the expression for V. Okay, so this is actually a follow-up of the earlier question. Okay, so it's the same circuit, but now you're following up with that. So we are supposed to find the current, supposed to find the current I. Okay, so we already found V. Now it's supposed to find I. Okay, so to find I, what we need to do is to find the total resistance. So we know that this 100 millihenry. So the impedance ZL will be given as J omega L, which will be J10. All right, so the total impedance in this case will be 30 minus J100, okay, parallel with 20 plus J10. And that will give me 22.7 angle 14.2 degrees, and the current will be given as 10.44 over 30. So this is from the earlier calculation, 16.7 degrees, and this is 22.7 angle 14.2 degrees. Okay, so 0.46 angle 2.5 degrees, and the expression will be 0.46 cosine 100 and t plus 2.5 degrees. Okay, answer C. Okay, so it's the same, again, same parallel resistance, Ohm's law, okay, only apply to phases. Okay, so question 29 and 30 are almost the same, only difference is the application in capacitor or inductor. So in this case, you're supposed to find the inductance, all right, given the phase angle. Okay, so we know that this is the expression for the Vs. So this is actually 7 angle 0 degrees, where omega is 2 pi f. So 2 times 10 to the power of 4 pi. So that is your omega. All right. So we know that the resistance, okay, the VR is found to be negative 67 degrees with respect to the source. Okay, so if I were to write the expression for the VR, okay, just like how we do a voltage divider rule, it will be 100 over 122 plus j omega L times the source, which is 7 angle 0 degrees. All right. Now, if I were to just put it together, so it's easier to see, 107 angle 0 degrees over 122 plus j omega L, correct? Now, for this 122 j omega L, okay, let me put it as polar form, so it's easier to see. So this will be 122 square plus omega square L square, square root, and the angle would be what? Inverse tangent of omega L over 122. All right. All right. So if I look at this expression now, there is the magnitude portion, which is this, and the phase angle, which is this. All right. Now we can ignore the magnitude portion because we don't have any information on the magnitude of the VR. We only know the phase of VR. So if I focus on this portion, the phase of VR, we can say that this value, which is negative, y negative is 0 minus this angle, right? Because in polar form, the numerator subtract the denominator. So this value is actually equivalent to 67 degrees. Okay. So in that sense, I can rewrite it as omega L over 122 is equal to tangent of 67 degrees. All right, so omega we know. So I just solve for L. I'll get the answer as 4.57 millihenry, which is C. Okay, so in this question, basically, we have two portions, correct? The magnitude and the phase. But since we are given the phase, we just use the phase information to solve for the unknown, which is the L. Okay, for the last question here is the same thing. Okay, only thing omega is already given to us as 100. Okay, and the angle is the same. I mean, the source is the same. So again, we have the same expression, 100 over 105 minus j over omega c times 7 angle 0 degrees. So we do the same thing, means what we'll get is we will have a magnitude portion which we ignore, and then we have the angle. All right, and we know that 1 over 105 omega c is given as 43.6. And with that, we can solve for C as 100 microfarad. Okay, so that basically wraps up all the questions, all right, that we have for this revision. Okay, so you can see that it does require you to think carefully exactly what you're supposed to do, but whatever formulas that you use to solve are all known to you, right? There's nothing that you have not seen before. Okay, whatever that we have covered in the studios, in the tutorials are the same concepts, same formulas, same techniques that we are using to solve the questions here. All right, so as long as you look at the questions carefully, you analyze the circuit and understand what they're asking you to find. Okay, one of the common mistakes that students will usually make is when they solve for the first unknown, they come to the conclusion that is the final answer. Okay, but maybe there is a second step involved. Okay, maybe they ask you to find voltage, but the moment you solve the current and you see that that answer is actually part of the options, you straight away take that is the answer. But no, okay, maybe it's just there to trick you. All right, so maybe they ask you to find voltage and the first step is to find current, and then you never continue. All right, so always look back at the question carefully to see what are they asking you to find. All right, don't assume that the first thing that you find is already the answer. Maybe there is another step, there's another step. Okay, you have more than enough time. Okay, you have, I think, 75 minutes and you have 12 questions, so you have more than enough time to work out, okay, and get the answer. All right, and it's open book. All right, so you're allowed to bring any material, hard copy material. Okay, so I said before, no hard copy, no handphone calculator. You have to use dedicated calculator. Okay, and it's open book, so you can bring whatever hard copy. You're not allowed to bring soft copy material. Okay, that means you can't say I put everything on my iPad, I just use my iPad. No. Okay, whatever that is hard copy, you're allowed to bring. Okay, other than that, yeah, come earlier a bit. All right, so you settle down and you know get yourself prepared so you don't rush in, if you are late or anything. Okay, so I think LT everybody should know where it is, correct? Any question that anybody wants to ask about the midterm or any other questions here? Yes, you're allowed to bring in whatever you want to bring. There is no restriction on the amount of material. Okay, does pencil have to be 2B? Yes. Okay, we will use, because we are going to give you OCR forms. Okay, so you're going to shade the answer. Okay, so if you use any other type of pencil and the machine does not read it, then it leads to a lot of issues, correct? Okay, so a 2B pencil will always work. It's the one that is recommended for the OCR form, so that when you shade it, we can get the correct reading from the machine. Yes, any kind of calculator, there's no restriction. So like I said, if the calculator can solve all these complex numbers, can solve everything for you, just go ahead and use it. All right, there is no restriction on what the calculator can or cannot do. Okay, so it is you'll be free sitting, all right, in a sense that you don't have to sit within your own class or your own lab group. Okay, but you need to sit wherever the papers are ready laid out for you. Okay, so we will have spacing between seats and so on. So just to make sure there's enough gap. All right, but you can just go in and sit wherever you're comfortable. Okay, so that's all I have. If there's any other questions, I will stay back and answer. If not, good luck, and I'll see you all on Saturday. Okay, hard copy material. Again, there is no restriction. You can bring whatever hard copy material you like. There is no restriction on that. Okay, question 6. Okay, so for question 6, like okay, so again, why we are able to separate the circuit is because the voltage drop that would be experienced across the load, this R, will only be a result of the current flowing through this branch. All right, and the current that's flowing through this branch will only be, or whatever, to put it another way, is the voltage drop or the Thevenin's voltage that is observed by this open circuit here would be a result of whatever you see in this components here, which is the 10 ohm, 20 ohm, and 10 ohm. All right, and the current that flows through these two components would be a result of current that comes out of this supply only. Okay, why? Because whatever comes out of here will come back here. All right, so even though there is a mix of current here between the upper circuit and lower circuit, when the current comes back to the 10 volt, it is whatever current that left the 10 volt. So it will not be any additional because of this other circuit. Okay, so that is why we can say that the Thevenin's voltage will only have to be calculated based on the 10 volt supply over here. We don't need to factor in the lower 10 volts. Okay, thank you. I'll see you all on Saturday.